Alrighty, so section 2, we're still talking about polynomials. We're going to start getting into polynomials of higher degree. So poly means many, again, nomials, terms, so many terms, looking at things that have x as their variable, but raised to only whole number powers. So to the first, the second, to the third. So we're going to look at higher degree ones today. So above degree 2, so not just quadratics, what happens and what are some of the things we can notice about similarities and differences between them. So our essential questions for today: how can I use transformations to sketch graphs of polynomial functions, so about their looking at some of those characteristics, and use the leading coefficient test to determine the end behaviors of the graphs of these polynomial functions. So leading coefficient, so we know what that means, the coefficient of the highest degree term. And the end behavior, we're talking about what happens at the ends of the graph as x gets really, really big and as x gets really, really small. So we call that the end behavior. So we'll talk about notation-wise, how do we talk about that? So there's just some things if we can notice right away, just some quick tests to think about what we know about the general behavior of a graph, that it's polynomial. All right, so let's talk about two main features of a polynomial function graph. So the two basic features that we need to always look for, they should be what we call continuous graphs. What that means, there are no breaks. You can draw the entire thing without lifting your pen or pencil, continuous. So there's no breaks, no undefined places on the graph at all. And everything has to be smooth, rounded turns. So no sharp corners. So smooth, rounded turns. So no sharp corners at all. So take a look at the four graphs, and I want you to decide which of these, based off of those two features, do you think would be polynomial functions? Or maybe it might be easier, which ones don't you think will be polynomial functions? All right, so pause the video, go ahead and see what you think of these four pictures. All right, well, first of all, this one's not a polynomial because it's broken. It's not continuous. This is what we would call discontinuous. There's a break in the graph, so that is not a polynomial. Sharp turn. They had to label it just to be sure. This absolute value function is obviously not a polynomial. It's a different kind of function. So this is not either because of the sharp term. The sharp turn. The other two are definitely polynomial functions. You could guess maybe what you think each of these degrees might be based on thinking about what you did last year in Algebra 2. We'll be able to look at this by how many times it turns, what the ends of the graph are doing, exactly what they are, but both of these two are actually polynomial functions. They are both continuous and they don't have any sharp corners. Everything's smooth, rounded curves. All right, so let's talk about some basic characteristics about these polynomials then that have graphs that look like that. Which one of the graphs do you think x to the 7th will look more like? Of our parent graphs that we've already talked about, x squared or x to the 3rd? What do you think? Which one do you think it would look more like? If you graph on your calculator, you can definitely tell, but what about gut instinct here? Which one? Well, it should look more like x to the 3rd, an odd degree, because that means positive numbers raised to a power that's odd will give a positive answer. Negative numbers raised to an odd power will give you a negative answer. So the behavior should be the same for both of these graphs. Now, will x to the 7th be a little bit steeper? Yeah, for sure, because if you take a number and raise it to the 3rd power, you're going to get a way bigger answer if you raise it to the 7th power. So it'll be a lot steeper, but it'll definitely look like x to the 7th, so, or x to the 3rd. It'll have that same basic shape. So even powers, when n is even, you get shapes, end behavior shapes that look more like this. So it's symmetric with respect to, so we'll use our little abbreviation here, symmetric with respect to the y-axis. In other words, it's going to look like y equals x squared. That's a kind of more like its parent shape. If the n is odd, it's going to be symmetric with respect to the origin. These are called power functions when it's just that one term, like x to the 2nd, x to the 3rd, x to the 4th. In other words, it's going to look more like the x cubed. So if you kind of keep that in mind, that'll tell you a little bit about what the ends of the graph should be looking like. So you'll have pictures like this. So those are called power functions. So we should be able to know by the powers what the basic shape is going to look like. Now, obviously, there could be more terms to this, though. That doesn't just have to be the highest degree term. So we're going to talk about the leading coefficient test. The idea here is that first term is still the most important. It tells us the most information about what the end behavior of the graph is going to look like. So we're always going to focus in on that highest degree term. The leading coefficient then is the coefficient of that highest degree term. So whichever one is the highest degree, that number is where you're going to look. Be careful, they may not be in order, right? So just be cautious that you are actually finding the highest degree term. So depending on whether you're degree is even or odd, the end behavior of the graph is going to be a little bit different. So we want to make sure that we understand what's happening as we look at this. So the leading coefficient test is going to tell us about the end behavior of the graph. Okay, so we're going to break it down then into odd and even. So if you can do that as well for your notes, that'll be really helpful. So if it's an odd degree function, so think in your head like the x cubed and the x to the 7th, it depends on what that leading coefficient is. If that leading coefficient is positive versus negative, it's going to affect the direction that it's opening. Remember, just like parabolas, right? If the A was positive, it opened up. If the A was negative, it opened down. It's the same thing for all these others. The end behavior is going to be different. So let's start with if the leading coefficient, I'm going to abbreviate here. This is the leading coefficient test. So if the leading coefficient, that A value, is positive. Okay, so if it's positive, that means it's going to be like normal, regular old x to the 3rd. Keep that x cubed in your mind, like y equals x to the 3rd. That's a great example for this one. So if that's positive, what does that mean for the ends of the graph? So what we're going to do is look at the right end of the graph and the left end of the graph. So I'm going to break this down into the right end and the left end. All right, so the right end of the graph, what I'm talking about is over here. This is the right end of the graph. So as the x gets bigger, what's the y doing? It's getting bigger. So both of them are increasing. So as the x gets bigger, the y gets bigger as well. So it's, in other words, it's increasing on the right. So it rises, a lot of times people would say. So it rises on the right. I guess that's the best term that you're going to be able to see if you want to call it something. But notation-wise, mathematically, how do we say it? So let's talk about what that means. So here's how we describe it. We're going to say what the function does. So f of x or the y approaches what as x approaches infinity. This is the right end of the graph we're talking about. As x approaches infinity means as the x's are getting bigger. That's what infinity means. What our job is to fill in this box. The value, the function is approaching. So when you see this little arrow, that you say the word approaches. So as f of x approaches what as x approaches infinity? Well, it's going up, right? It rises on the right, which means it's also approaching infinity. That's what the arrow means, that it's getting bigger and bigger. So notation-wise, to describe rises, we have to say that it goes to infinity. That's what that means. That's the right end of the graph. Okay, now let's talk about what the left end of the graph does. You have to look in the other direction. For the left end of the graph, as the x gets smaller, what happens to the y's? They go down. So it falls, I guess, is the best way to describe that. So on the left side of the graph falls. It's falling. It's going down. It's getting smaller. So think about when you do end behavior, it's like you're standing in the middle of the graph and you're looking to the right, and then you look to the left. You're looking in both directions. How would we describe falling? Well, the rest of the sentence is exactly the same as what it is for the right-hand side. X approaches negative infinity though, right? We're looking in the other direction, so negative infinity. So everything else is kind of laid out. The format wise is the same. F of x approaches blank as x approaches negative infinity. So again, that arrow means the word approaches. So here's what we need to do then. We got to fill in that blank. Well, what is it doing? It went down, remember? It fell, it falls, or fell, or however you want to say that. So it's approaching negative infinity then. So we're filling in that other box. So that other end of the graph, the end behavior we call that, it's going down on the left and it's going up on the right. So if you can think about rising and falling, that's the main concept. Then you just have to write the notation to describe that. So what we just did here, this is called the end behavior, what's happening at the ends of the graph. So I'm kind of short term here. The right, it rises, the left, it falls, and then how do we say that notation wise is what's after it in the blue. All right, well, that's what happens when the A value, that leading coefficient, was positive, right, for the odd degree. Let's talk about what happens when it's negative. So we're going to do that perspective as well. All right, so what happens when the leading coefficient, that AN, is less than 0? Okay, well, that means it'd be like opposite of x cubed. Well, that's a reflection over the x-axis, which means the graph would look like this. So we're going to keep that picture in our head when we describe this. And again, we're going to look at what happens on the right and what happens on the left. So we're going to look at both of those. So what happens on the right side of the graph now and what happens on the left-hand side of the graph. All right, let's talk about the right-hand side of the graph. So the right-hand means as x is getting bigger, what's the y doing? Well, it's going down. It's falling. So it's falling, or it falls. So on the right side of the graph, it's falling. And then let's talk about the left-hand side. As the x gets smaller, so as the x is going that direction, what happens to the y's? They're going up, so it's rising. Rises or rising, however you want to say that. So it falls on the right and it rises on the left. So it's the exact opposite. It's flipped. Well, of course, if you make that leading coefficient negative, that's what's going to happen. Let's see if we can fill in the notation. The right and left-hand side notation is always going to be the same. F of x approaches blank as x approaches positive infinity. Why is it positive? Because it's the right-hand side of the graph. X was getting bigger. So the right-hand side sentence like this is always the same. The left-hand sentence also the same. F of x approaches infinity, as it was for the last one, as x approaches negative infinity. That means left. So whenever you see positive infinity here for the x, that means the right end, and then negative infinity means the left. Just think about what direction you're looking. All right, so what happens to the value of the function again? Let's fill those in. On the right-hand side, we said it falls. It was going down. See our arrow there? That means negative infinity. Kept getting smaller. On the left-hand side, it rose, though, which would be positive infinity. So the only part of this sentence that you ever have to fill in is what the value of the function does. So f of x approaches negative infinity on the right, and it approaches positive infinity on the left. So we can see what's happening. So odd degree, the ends are always going in the opposite direction. So think odd, opposite. Even, a little bit different scenario. All right, so I'm going to clear a little room here, and I have my old work saved. But let's go back to the even degree now. So we're going to do the same thing, but for even. I'm just going to move that over. So we're going to look at when the an is greater than 0 first. So that means think about like a regular parabola then, like y equals x squared. So the ends are doing the same thing. So we're going to look at what happens when the a is greater than or equal to 0. So that's the leading coefficient now, remember, the a value. All right, so let's look at the right side of the graph, and we're going to look at the left side of the graph. So we're going to look at both. All right, so as we look at the right side of the graph, as the x gets bigger, what happens to the y's? Well, they're getting bigger. So it's rising, or it rises. On the left-hand side, as the x got smaller, what happened to the y's? They still rose, they still went up, so it rises on the left as well. So for even degrees, we notice that the ends do the same thing. Because if you take a negative number and square it, you're going to get a positive answer. If you take a positive number and square it, you still get a positive answer. So we can fill in those end behavior sentences. So f of x approaches blank as x approaches. Now these are the same sentences. So right-hand side, the right-hand side, always x approaches positive infinity. We're going to the right. And then for the left, f of x approaches blank as x approaches negative infinity. Remember, negative infinity means looking to the left, like you're standing at the origin and you're looking left. What is it doing? It's rising again. So both of those rise. So the end behavior, we're filling in the same blank here. They're both going to be positive infinity. All right, let's take a peek at what happens then when the leading coefficient is negative. So what happens if the leading coefficient, that an, is less than 0 for an even degree? So think about a parabola that has a negative side in front. If the a is negative, well, that means it's opening down, right, when we look at that graph. So when we talk about what happens on the right-hand side and what happens on the left, they're still going in the same direction. They're just both falling. So as x got bigger, the y went down, so it falls. And as the x got smaller, the y still went down. So it falls on both ends. All right, so let's write that end behavior then. F of x approaches blank as x approaches infinity. That's the right-hand side. Remember, positive infinity always to the right for the x. And f of x approaches blank as x approaches negative infinity. Those two sentences never change. It's what you're looking for, the value of what the function does. It's the f of x part we need to fill in. They both fell, right? They're both falling, which means they're both going to negative infinity. So for the even powers, the ends do the same thing. For the odd powers, they go in the opposite direction. So looking at that leading coefficient and the power, those two things together tell you everything that you need to know. So the an is going to tell you if it's opening up or down, what's happening there. The degree is going to tell you if the ends are doing the same thing or if they're doing different things. So let's see if we can analyze a couple here and see if this makes sense. Take a peek, be careful. What I'd like you to tell me right here is what is the leading coefficient, and then what is the degree for this polynomial? So go ahead, take a moment, pause the video, see what you can find out. All right, so leading coefficient, -4. The degree is 6. Got to be super careful on this one because they kind of hid this highest degree term at the end. It was not in descending order, so be careful that you scan through everything. All right, so what does it mean if the degree is 6? Even, that means the ends are going to be going in the same direction. What does it mean if your leading coefficient is negative? Well, that means it's going to be reflected. So my leading coefficient is less than 0, and it's an even degree. So I know what my end behavior is going to be doing then. I'm looking at this situation, right? It's going to be opening down the ends of the graph. There may be weird stuff happening in between, right? It could be increasing and decreasing in between, but we're talking about what the end behavior of the graph is. So when they say the right hand and left hand behavior, that means the ends of the graph, right? The end behavior of the graph. So we're going to look at both ends. So let's talk about the right hand and the left end. Okay, so the right, we're going to use words and then we're going to use symbols. So for both of these, they're both going down. So the right end falls and the left end falls. So that's verbally, that's a verbal description. Now let's do the notation. F of x approaches blank as x approaches infinity. There's your right end always. F of x approaches blank as x approaches negative infinity. Okay, so since they're both falling, what do we use for falling? Well, negative infinity. It's going to get smaller and smaller and smaller. It's all about the degree and that leading coefficient. Okay, I want you to try these two. Describe the left and right hand ends of this graph. So please take a moment, pause the video, try them on your own. Look for the degree and the leading coefficient and see if you can identify what those are. All right, so for the first one, part A, leading coefficient. So this is the highest degree term is a 1/4, and the degree is a 3. So it's odd, and this is greater than 0. So what does that mean when it's odd, greater than 0? Well, it means we've got one of these kind of graphs. It's very much like just the x to the third. So for the right hand, it's rising, so it rises. The left hand falls. All right, so we have to describe those in our two sentences. So for the right hand, f of x approaches blank as x approaches infinity. See if you can fill in that blank if you haven't already. F of x approaches blank as x approaches negative infinity. The right-hand side, we said it was rising, right? Anytime you say the word rises, the value of the function is increasing. That means it goes to infinity. For falls, for the left-hand side, that means it's going to negative infinity. So this is just a typical situation. Leading coefficient is positive, so it's not reflected, and the degree was odd, so it's going in opposite directions at the end. All right, let's take a look at the second one. Leading coefficient, double check. This does look like it's the highest degree term. So the leading coefficient, -3.6. That means that an is less than 0, and the degree is 5. Okay, so that means it's odd. So it's very much like the last one, but because it's less than 0, that means our end behavior is going in the opposite direction. It's reflected over the x-axis. Now again, it may do some other weird stuff in the middle because of these other terms, but the ends of the graph are definitely going to do that. So what is it doing on the right? So as we go this direction, well, it's going down, it's falling. So the right end falls. What does the left end do? Well, it rises. So remember, they're going to go in opposite directions, always, if it's an odd power. Now, this is just a flip, though, of what we just did. So for the right end, f of x approaches what? As x approaches infinity. And then the left end, f of x approaches what? Blank. As x approaches negative infinity. Those sentences are always the same. What you're filling in is what the function does. It falls on the right, falls. Whenever you say falls, going down, negative infinity. On the left, it rises, so positive infinity. So our quest today is just to be able to describe end behavior. Being able to look at, we'll go back to our essential questions, that leading coefficient test to help us have some idea of what's happening at the left and the right ends of these graphs.